So, hey everyone, it's me, Deepak. So today we will be looking into this problem that is binary tree level order traversal. So what we are gonna do now? So here we are about to do something super powerful today. We are going to make this tree talk to us level by level. So what does this question ask to us? That is, given the root of a binary tree, return the level order traversal of its nodes value, that is from left to right, level by level. What does this mean? So here, as you can see, level by level means this is the first level, this is the second level, this is the third level, and here saying go left to right means, let's say I'm at the level 1, there is only one node, that is 3. Then in the level 2 there is two node, and I have to visit it from left to right. So after 3, the very next node which I'll be visiting is 9 and then 20. And on the next level, so here as you can see in the level 3 there is only two nodes, but I have to visit from left to right, as 9 doesn't have any child, so there is nothing to traverse over here. So the very first node in the level 3 is 15, that is from left to right I have to go, and the next node is 7. So the traversal will be 3, 9, 20, 15, 7, as you can see over here in the output. Cool. So let's look into an example for in-depth understanding to find the intuition behind it. So let's say consider this example over here. Cool. So think of this tree like a bunch of people standing in rows. Row 1 has the boss, node 1. Row 2 has managers, 2 and 3. Row 3 are the employees, 4, 5, 6, 7. And row 4 are the interns, let's say 8, 9. Just consider this. So here in the level order traversal, it's like if you had to shake everyone's hand row by row. Let's say there is an event in an office. So here you have to shake hand everyone row by row. So the prioritization will be obviously manager, and then we'll come down to the interns and all the stuff. From the boss will start, then manager, then employees, then interns. Cool. So here you have to shake everyone's hand row by row, starting from the top row, going left to right, no cheating, no skipping ahead. And we are gonna do this in the most systematic computer science approved way possible, using a queue. Yes, the same queue that you hate standing in at the railway ticket counter. That is first come, first serve. This queue is going to save our life. So let's say for example you are in a cinema hall. Over there are many people watching the movies. So here, let's say you want to find this guy, and the only way in general will be like in looking at for searching for looking for this person, this boy. But here, let's say what I could do in the according to this question, I will first look into the first row whether this blue t-shirt guy is there or not. Nope. Then I will visit to the second row. Then I will visit to the third row from left to right. Okay. After this girl, beside this girl, I found my person. I found the target target element. So in this way, we have to work on. This is level order traversal. But here, uh, is what is we are using the queue. But why we are using the queue over here? Because level order traversal, it is which we need to do, is basically a handshake line. Just now we uh, consider an example where we need to handshake the everyone or into according to the row. And in the tree is, I can also say that in a hierarchy. So whoever comes first gets processed first. Simple. And then it's like parents enter the line, then the children get in the line behind them, and so on. A perfect first in, first out scenario. If I had to use stack here, it will be like saying last person who just arrived suddenly cuts the line, because stack is what? Fif, philo, that is first in, last out, or I could say LIFO, last in, first out, which violates our condition. So here, let's say one came first, then it will be considered at the very last, which should not be the case. I have to do the level order. So level order is the level 1. What is the 1? So 1 needs to be considered. Okay. But if I'll be using the stack over here, the very first node which I will push is 1. but the it will be popped out at the very end. That's also the reason why we're using queue data structure over here. So here in the stack, it cuts the line and gets served first. That's the chaos, not level order. So here queue gives us order. Queues gives us discipline. Queues is literally the bouncer of this algorithm, making sure everyone stays in the line. So if I could say why I'm using queue again, then let's say imagine you are distributing ice cream. First come, you give to the root node 1, then you go to the node 2 and 3, then after that line there is 4 and 5, then 6 and 7, and then 8, then and 9. Proper fairness will be there. Cool. So let's say consider the example over here. So here I do have this tree over here. Cool. Because we know that we are gonna use queue, then why you are using queue? Let's say over here this is my queue, uh, under the right. So the very first node which I'll be having is the root node, and that is what 1. So I do have access to the only very first node. As you can see under the question, uh, there is only root node which is passed as an argument for this parameter or to this method. So I do have access to the very first node only. So what I'll be doing, I'll be pushing this, I'll be offering this queue, this node onto this queue. Cool. So I'll offer this node 1 onto the queue. So I'll check whether does this node, that is 1, have left child. Yes, it has one left child. So I will offer that as well to the queue. Then I will look whether this node has right child. Yes, it has right child as well. So I will push that too onto the queue. Cool. And so the moment, so here 1 is done. So I'll put this onto the list. Let's say for example I do have list over here under the list, which will determine what all nodes I have traversed till now. Cool. So here I have traversed 1. Cool. It's done. I have traversed 1. Cool. And then what do I have to see? Okay. Now I will this node is traversed, so I will bring this node out of the queue. And then what node I do have? That is 2. As you can see over here, it's first in first out. Now after 1, the chance will be for the 2, not the 3, not the 3. If I'll be using stack, then in that case I need to give chance to 3, but here 2, which is what we are abiding the rules of the level order traversal. After 1, only 2 has to be traversed because it's level order traversal. So here now I'm at the level 2, and from left to right, the very left node is the 2. Cool. Now here I'll be considering 2. Now we'll click. Okay, whether does 2 has left child? Yes, it has the left child, 4. Cool. So offer that left child to the queue. Does this 2 has the right child? Yes, it has the right child. Offer that as well to the queue. That is 5. Cool. Now does 2 has other child? Because it's the binary tree, it will be having at max 2 children only. Now it's done. Cool. So let's go for the next iteration. Now at the very first position, what do I have? 3. Let's consider this as the current node 3. Now does 3 has left child? And also we need to put this onto the queue. Whatever I'll be popping out, whatever I'll be doing the poll from the queue, I need to push it. Cool. So here does 3 has left child? Yes, it has left child 6. Cool. So then push this onto the queue. What is that? That is 6. And now does this 3 has right child? Yes, it has right child. Now offer this 7 node has also onto the queue. Cool. So now this refreshing current node, that is 3, I have looked onto the all the childs of it. Cool. Now the next node which I have to look is what? Is 4. Now the current node is 4. So it will be onto the list because this is now done, visited. Cool. Does this 4 has left child? No. Does this has right child? No. So nothing is there to visit. So I'll be simply moving to the next node. Cool. What is there? That is 5. Now 5 is the current node over here. So does 5 has left child, and now it's traversed as well. By the way, it's visited. Now 5 has left child. Yes, 5 has the left child, as you can see over here. So I'll offer this left child onto the queue. Cool. Now I will put the left child, that is 8, onto the queue over here. Now does 5 have the right child? As you can see, there is no right child over here, so there is nothing. So I'll just simply move ahead to the next node, and that is what? That is 6 over here. I'll now it is visited. Now I'll put this onto the list. Cool. And the current node is obviously now 6 over here. Cool. So now does 6 has left child? No. Does 6 has right child? No. There's no node at all, so nothing to do. Just go for the next node. What? The next node, that is at the first, because of the queue, first and first out. What's that node? That is 7. Okay, take that out. Now the current node is 7. Now it's I'm considering this for now. So it's traverse is visited. So now does 7 has left child? Yes, it has the left child. Cool. So offer it to the queue. Okay, so I'll offer it to the queue. I'll put this onto the queue 9. Okay, so does okay, so now what do I have to check? Does it has right child? No. So there is nothing to offer onto the queue. Cool. Move ahead. Now what else is there onto my stack? 8. 8 is the current node for now. So now it's traverse. So I'll be like, okay, 8 is there. Now does 8 has left child? No. Does 8 has right child? No. Nothing. So nothing to do. Go ahead for the next node. What else is there? 9. 9. So I'll be taking out 9. So now it's visited. So I'll be checking whether does 9 has left child? No. Right child? No. There's nothing. So I'll be going ahead for the next node. So is there any node left onto the queue? No, there's nothing. So I don't have anything to traverse for now onto the queue. So the moment queue is empty, all the nodes is traversed. So as you can see over here in the list, you can find that we have traversed row by row, that is level by level, from left to right. As you can see, 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. We have traversed it in a level order traverse. We have traversed in the level order using Q data structure, and this algorithm is also called a breadth first search, because uh, unlike DFS, we are not going depth, depth, depth. If I'll go depth, then it will violate condition, because I have to traverse the whole level first. It's like, let's say in a you are studying, there might be the case that, let's say you are studying data structures and algorithm. Let's say you're like, let's study arrays data structure. That what in depth, what is arrays data structure, what are patterns are there, what are problems are there. You are solving hundreds of problems. Then you're jumping to the stack data structure. You're learning what is stack, what are the patterns, how, what are the nuances. You are solving hundreds of problems over there. Means you are going depth for each topic. Just like this, what does this node have? I'm going depth. And another way is like, you are studying arrays, you are doing some classic problems, you are moving to the stack. Doing some classic problems, you are moving to the skews, you're doing some classic problems. And then after having the proper good idea about all the data structures, you are coming back for the mastery for each. It's like level order traverse. You're having a bright idea of it. That is what breadth first search. Okay, cool. So now we have understood, we have done the dry run, we have get the intuition, we have built our brain muscle that why we're using this, how to do this, and all the stuff. And also I want to let you know that uh, that here, mm, it's like why I'm not gonna use the recursion. Cool. Because if I'll use the recursion, it will make our code complicated. It will make everything complicated. I need to do write the extra code hassle for that. That's a different thing. Okay, we can write the extra code, but it will get more complicated, and it's obviously not good compared to this approach of using the queue data structure. Cool. So for the time complexity, as you can know that here every node is n-queued once and d-queued once, so total operations is big O of n, where n is what, where n is number of nodes. And also for the space complexity, in the worst case the queue can hold all nodes of the last level for a complete binary. Here I don't have the all nodes, but let's say for the complete binary all nodes it does hold. So in that case, the last level can have n by 2 nodes, so space complexity is big of n only in the worst case. This is the trade-off. That is, we spend extra space to guarantee level by level order. So here, as I said that we are not using recursion over here, because if we tried recursion, we would need to track levels manually, which is extra work. Queue naturally maintains order. I don't need to do the explicit work. Queue naturally maintains order. Parents first, children later, exactly what we want. That's why we used queue over here. Okay, cool. So now it was all about the theory part and all about the intuition. Now let's now the code will be nothing for us because we know everything. That's what we need to do. Code is like a piece of cake where you know the whole story behind it. So let's do the code as well. Cool. So here what it's asking to return list of list integer. What does this mean? So here the inner list integer is what in each level, as you can see there is two nodes. As you can see here, there is at level 3 there is four nodes. Over here there is four nodes. So here there is not a single node, there's a list of no, list of numbers, that is list of the nodes at each level. So here I do have for the height, for the number of rows I'll be having the list, and in each row there will be number of nodes. So that's why there will be list of nodes as well. For the list of heights I'll be having the list of nodes. That's why I have over here list of integer over here. So for the each row I'll be denoting with list of integer. So I need to return this. So firstly I need, so that's what it return type is. So I need to put that. Cool. So here I can, so here I need to return the integer, that is a value only, not the uh, row itself. So this is what, let's say for example I'm saying traversal, which I have done, and let's say here I'm taking the array list implementation. Cool. Now what if root itself is null? There's nothing to traverse. If root itself is null, what else I can do? I will just simply return an empty list. I can't do anything over here. Cool. And as we know, we need queue data structure over here. So let's create a queue as well. Cool. uh, let's say it will be holding three node defined over here. Cool. And let's say name it as queue only, and it's an implementation of array dq. Cool. Now the very first node which I have access to is root. So let's offer this to our queue. Cool. Now as we know that we have to do all this story which we have done just now until our queue is empty. Cool. So let's write that condition that until our queue is empty, I have to do this thing. I have to do my operations which we have done in the dry run until queue is empty. Cool. So here I need to maintain the list at each level. So I'll be requiring the list of the integers, value, that is values I have found at each node. So here let's say current level is what this is this. Cool. That's what we do want over here. And now for this I need to know that at each level what's the number of nodes I do have. That's the number of nodes will obviously the queue size at each node. Yeah. So that I'll be doing over here. So I'll be traversing till there. So here the queue dot size and until I is greater than 0 because the indexing starts from 0 and then I minus minus over here. Cool. So here I I should be aware of the current node because here we know that we were finding out the current node and then we were refreshing to its left hand child, does it exist or not. So here the current node will be this. I'll be getting from where I'll be doing queue. I'll be taking out from the queue. From here I did take out, if you remember. Cool. Now I have found a current node. Now it's traversed that what I did say. If it's traversed, then in the current level I should add it. That is add this. I need to add the value of it. So here current dot val. Why val? Because here it's provided the internal implementation for the tree node val holds the value of the node, and then I need to check the left and right which we are doing over here. Which we are doing over here. Left, right, does it exist or not? Okay, exist, then put on the offer to the queue. If it doesn't exist like this in the tree, then don't put, there's nothing. If it there is only one node, then do accordingly. That's what we did. So here we need to check the left and right. If current dot left is not equals to null, in that case what we can do is queue dot offer current dot left. Cool. And then the same thing we need to do for the right as well. If current dot right is not equals to null, I'll be offering that as well to the queue. That is current dot left, queue dot not wrap is right. Cool. And after this iteration, what does this mean? It means one level is done. One level is done. Now put this whole level, whole list onto the list of height. Cool. It's like this. I need to put this current level onto this traversal. See here, I'll be doing traversal dot add this current level from over here. Cool. And then at the end, what is asking list of list integer, that is what traversal. Okay, this thing. Okay, so here I'll be passing returning that only. Return the traversal which we have did